Hi, I'm Jeff Nolan. Welcome to Now, Next, and Beyond. Today's episode is all about crystals with Dominic Loiacono. I've been wanting to do this episode from the very beginning of this podcast because crystals are totally fascinating. And I'm not talking about some rocks mined in an exotic location, cracked open and displayed on a gift store shelf somewhere. No, these are manufactured, grown crystals in a state-of-the-art facility. And they're very often not found in their finished state in nature itself because we dope them. We change their properties for the desired application. Now, crystals are really critical for all things photonics, whether you're talking about lasers, optical communications, instrumentation. Crystals are essential gear. And the process of growing them is, to say complicated is an understatement. It's also incredibly energy intensive and requires an inordinate amount of expertise to do it successfully. We're going to talk about all of that and more. Something else to think about is, when we talk about optics and, crystals, that part is kind of easy to grasp. But then let's move over to the engineering materials side of the business, which is things that, elements of the periodic table that don't normally go together. So when your chemistry teacher told you didn't need to know any of this stuff, well, you kind of do. Gallium arsenide, silicon carbide, these things don't go together. So we had to come up with novel techniques and manufacturing capabilities to bind them together in a permanent and stable state. And here again, we lean on the expertise of growing crystals to achieve that. So looking forward to this. Please, I'm happy to hear your feedback and comments. Let's just get on with it. Hi, welcome to Now, Next, and Beyond. I'm Jeff Nolan. Welcome to our episode on crystals. This is a topic that I have wanted to dig into, but even before we had a podcast. This is so fascinating. And with us today is Dominic Loiacono, who is the Vice President of our Crystals Division in our Materials Group. Welcome, Dominic. I did your bio all up front, so we can skip all that. But I got to ask you this. Your family name is storied and synonymous with the crystals industry. Tell us about your family and how you became such a dominant force in this industry.
Sure. Thanks, Jeff, for this opportunity. Well, it all started with my dad, Gabe. Back in the 50s, he was one of the first growers at Bell Labs in Murray Hill, New Jersey, to grow lithium niobate, which is a nonlinear optical material. Then he went on to start a company called Crystal Associates in around 1975-ish, which then was acquired by Coherent in late 2000. Now, so clearly in my family, right? However, at an early age, about 9 years old, I kind of got, I don't want to say brainwashed, but every good parent exposes their kids to a lot of different things. So at age 9, I got a Gilbert Chemcraft chemistry set. It was this big thing with yellow double doors, test tubes. It was the cool wobble, right? So that was kind of like my first introduction to science, chemistry, materials. And basically, I want to say because of that, it kind of really, I became very curious about things, materials. And that most likely is the reason that led to my passion for science, chemistry, and technology. I then went, did well. Science and chemistry just kind of came natural to me, kind of like breathing. And I did my undergraduate at Seton Hall in New Jersey, and then my graduate work at Stevens Institute. While I was at Stevens Institute, I got my first tech job at, again, where my dad worked at Bell Labs in Murray Hill. And I was there for about 6 years. Then I actually left Bell Labs to join my father's company, Crystal Associates, in about 1996.
That's awesome. So it's funny because in the year 2024, when somebody says, "Oh, my dad was a grower," you have a whole set of different, you got a whole range of other images that come to mind. And I promise you this, I commit to you this, there will be no Breaking Bad references in this entire podcast episode. So where are you located?
We're located in Bud Lake, New Jersey, in Morris County, New Jersey, which is about, to put the pin in the map, about 50 minutes west of Manhattan.
So how did a fine Hawaiian family, Loiacono, end up in New Jersey? It's an inside joke. I know you're not from Hawaii, but
Yeah,
uh,
yeah. The Loiacono family came over from Sicily. I think sometime early 1900s. My grandparents were born in Sicily on one side, and then my other side is Napolitan from Naples, Italy. And so when I get angry, I sing about it.
yeah.
Something like that.
So tell me this. So your area of science is kind of it's 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 interesting to me because it kind of is a little bit discrete, a little bit it's process manufacturing. It's the physical science, but it's really wrapped up in a lot of arcane knowledge that gets acquired over time. What is it that somebody needs to possess as character traits to be successful as a crystal grower?
Well, I think it's very interesting. It's a great question. The first thing, it might not seem obvious, but curiosity. Why? What makes this work? Why does this crystal look green? Why does it blow up in a laser? Right?
Yeah.
Curiosity. Then the other thing is uh, an idea of sense of urgency, where you want to know why. You're curious. You want to know why. Those traits are really paramount.
Yeah, I would imagine that that curiosity also has to combine a lot of intuition because when that laser does blow up, all you have left is really essentially the debris. You don't have, there's not a lot of evidence beyond that about what went wrong. So you have to intuit what went wrong, form that hypothesis, and then try it again.
Right. Correct.
So let's talk about crystals as a product now. So,
Sure.
aside from so crystals, I think in popular culture, they have this like whimsical and mystical set of properties to them. But,
Right.
and obviously they're used in fashion jewelry, they're an accessory. But what are,
Sure.
in the world we care about, what are crystals used for?
Well, there's three types of crystals, really. Um, there's optical crystals. There's crystals that are used for, or in like we're talking about here, main focus is lasers. Those are like photonic crystals. And then there's a whole nother ginormous class, semiconductors, right?
Right.
Semiconductor crystals. And, what they're used for is, the optical crystals are used for optics. The photonic crystals are mostly used in lasers and to make wavelengths of light into something else. And semiconductors, silicon, gallium arsenide, the two largest, semiconductor or electronic industry. That's why computers exist, transistors, that kind of thing.
So in those semiconductor crystals, you're basically taking different elements that don't normally go together and figuring out how to bind them, right? So the crystal itself becomes the glue that holds these things together. Is that accurate?
Correct. Yeah, correct.
Okay. So I mean, Coherent, we play in all of these. In fact, and all the different techniques for manufacturing them. But let's talk about optics first. So,
Sure.
our if we take our primary focus, pun intended, optics, what properties do crystals bring to optical devices?
Well, I mean, they have the ability to change the wavelength of light through nonlinear processes. They also have the ability, you'll hear me use the term gain crystals, which
Right.
basically that's actually what makes coherent light, which is basically having the same wavelength and phase to make a laser light. Um, that type of gain material.
Okay. So, and doping is a really big thing with crystals as well. You're imbuing them with properties they wouldn't
Sure.
natively have, right? So, tell us a little bit about that process.
Yeah, well, doping is akin to flavoring your food, right? Sorry for all the analogies here, but I think it might help. Um, yeah, I mean, you add things, dopants, to crystals to change their fundamental properties. There's some reasons why the crystals won't work, like a laser crystal, like yttrium aluminum garnet, or called YAG, uh, doesn't doesn't make laser light. However, if you put a rare earth neodymium in there, now you can actually generate coherent laser light if you hit it with what they call pumping light.
Okay. So in that process, what value then does the crystal itself provide if it can't do the thing that you want it to do absent of the doping?
Uh, Not much, right?
So
I
it's
mean, you're
just there's a
actually
medium
taking
to hold.
materials. Yeah, it's all about. It's kind of like, again, like baking a cake. You have flour and water. Okay, that's bread,
Right.
right? How do you make a cake? Oh, let's put sugar in it. That's
Yeah.
like the dopant, right?
Yeah. Yeah. Well, I'm all and anything that's a delivery vehicle for sugar, I'm generally a fan of, so we're good on that. Uh, are there any unintended consequences of doping crystals?
Oh, sure. Um, when you so let's use, again, I keep going, I'll go back to YAG as an example. So YAG has a very high thermal conductivity and a very high index of refraction. So that's a good use for what they call like pure yttrium aluminum garnet, or YAG. When you put neodymium in it to make it a laser host and generate laser light, it does two things. One, it causes absorption bands, so absorption. Some you want, some you don't want. And then I mentioned that it has this nice higher thermal conductivity. It lowers it like 30%, quite a
Wow.
bit. So, there is unintended consequences to doping or making materials less pure. But let me just also show you where it's like really, really needed. Obviously, in a YAG crystal to make it laser, but in a semiconductor, if you have silicon, you need to dope it to change its electrical properties for it really to be useful. Right? The same thing with gallium arsenide and other materials. So
Okay.
dopants are kind of like flavors to your cakes.
Okay. And the dopants, I know they're typically rare earth minerals are the most common, but are there other dopants that are not rare earth minerals?
Yes, I mean, you can change the properties, the conductivities of materials by just pretty much the entire periodic table.
Oh,
Things go in to your mix or into the crystal structure based on what you're trying to substitute. Sometimes they're happy to go in, other times they don't go in. The actual act of crystallization is actually a form of purification. So crystals, if you keep growing crystals, and you just make them pure and pure. So sometimes you have to, force the dopants to go in.
oh, yeah, that's interesting. Okay, so and then for lasers, photonics, I mean, you just said, I mean, without crystals, you don't get the gain for laser light. So crystals and laser sources go together like peanut butter and jelly. So you can't have.
Yep.
And actually, that's one of the things
Yep. That's
about
cool.
photonics that I learned when I joined Coherent originally is it quickly became apparent to me that it's equal parts the laser science, mechanical engineering, how to put all the stuff together, and the optics to not only gain the light but then deliver it to the right place. Because you look inside one of these boxes, and there's a lot of optics that are directing those beams or combining them or doing something else to them to get them in the form that is necessary to do the work. Which actually brings me to a question. So beam combining, how does that work?
Well, beam combining, you can do it multiple ways. You can basically create angles, and you have index of refraction. So the light bends, and then you can combine that way. You could just take two beams, put them into an optic, and combine them. But you also could take, what I mentioned earlier, pumping, right? Using non or incoherent light to make coherent light. You could have a big array of stuff and pump from all around. So that's kind of combining all the light energy and then coming out with a single laser beam.
And then I read also that crystals can store energy. And again, this is not the mystical kind of energy, but can store electrical energy, like a capacitor. Is that a problem inside of a laser?
Um, Sometimes yes. When you have laser light going through a material, you can generate an electric field, and then vice versa, you could put an electric field on a crystal and generate movement, actual movement, or piezo electricity.
Oh,
You could, piezo is a material that you put a voltage on and you get a deflection. Also, um, quartz crystal oscillators, which has been around much longer than my life.
yeah.
Uh, Basically, you could put a voltage on that, and that causes an oscillation, and that oscillation is the fundamentals for frequency keeping and time keeping for many, many, many years.
The mystery of a quartz wristwatch unraveled.
Yeah.
Yeah. Okay, so does that mean that crystals could eventually be like a battery?
Um, Not necessarily. They can. They're better at converting mechanical stuff to electrical stuff, but not really energy storage.
Got it.
Maybe data storage.
Oh, yeah.
There's, you've seen, the Superman movies. He's got the little crystal from his
Yeah.
dad, puts it in the thing, and it's got,
Yeah.
the whole history of the universe in it, right? And there's a little crystal because you can actually uh, create defects or ones and zeros at the atomic level. So you can imagine you can have maybe billions or trillions of information in a small crystal, and there's a lot of work done within that field.
This is the thing that gives me hope for humanity is the capacity for human beings to innovate and come up with things like this. I'm like, this is why the future will actually be better, I believe. It's amazing.
Agreed. Yeah.
Okay, so I'm going to assume, okay, now let's jump forward. Okay, so I'm sure that a lot of people listening to this who are unfamiliar with the idea of manufacturing crystals kind of operate on the assumption that these elements, you travel all over the world, you find these exotic locations, says, look, I got this crystal here. Then you get, you start digging and you mine them out, and then there's guys carrying them in baskets, and then, we transport them to where they're needed. But that's not it at all. In fact, the crystals we use in the kind of industrial applications, they're manufactured. They're, well, for lack of a better term, they're grown, right?
Correct.
All right.
Growth. Yeah.
Who figured out how to go back to the beginning? Who figured out we could do this?
Well, I'm a little bit of a history buff too. Not just like the ancient alien things, but the Sumerians. There's records, probably some of the first writings of the Sumerians, like 6,000 plus years ago, and they actually make reference to magical formulas based on substances that later we figured out are crystals. Then you have the Egyptians, jewelry, and then you go through history with probably the largest mass production was probably the quartz crystal shortly after World War II.
Okay, but when we go back to the Sumerians and the Egyptians, so you're really saying it was aliens?
Well, I mean, the oldest crystal known on Earth is zirconia based or zircon, and it's like 4 billion years old. When the Earth cooled, it created.
Yeah.
So, but no, that'll be a different cast on aliens for sure.
Okay, so and I want to revisit this one question I had that I kind of asked but then skipped over. I'm assuming that every crystal we manufacture is in fact a replica of something that exists in nature. Is that true or not true?
Well, I actually got a little show and tell. So,
ooh, this is gonna be our first
here's
show and tell.
Yeah, so here's some Lomanite, and here look. So Mother Nature made this hydrothermally, which is basically really hot water under high pressures in the earth, and then it cools, and out this stuff comes. But not if you look at it, you can't see through it. Not much light gets through that. Right. I did mention quartz. Here's what they call smoky kind of quartz. There's a whole lot of dopants that go in it, and Here's some quartz crystals. But again, you see there's lots of cracks and crevices and
Right.
the color is beautiful stuff. Right? Very beautiful stuff. But to use it in optics and laser and photonics, you really need to produce things like this. Okay. Now, that is what we've actually grown in New Jersey. It's about 2 kilos. It's grown from a small seed in the middle there, which you can't quite make it out. But
Right.
notice a few things, right? Super clear, no real defects, right? So low defects, low absorption makes all laser components happy for sure.
And that's how it came out of the machine, looking like
Yeah,
that.
so these are actually, or the grower,
Right.
right? So this is grown by a method called flux growth, where basically you take a seed, you put it in a hot lava, and you do everything right, make it happy, cool it down, and out comes this sucker in about 6 months.
Wow. 6 months.
And these are natural crystallographic facets.
And just to be clear, 6 months, every minute of every day in that 6-month process, something can go wrong.
Yes, unfortunately. Again, I'll use another analogy. Crystal growth is like flying a plane. You got all your instruments, you got your temperature controls, you got your altimeters, all that stuff, right? You do everything the same. You use the flight book. Everything's the same, but no 2 flights are the same. No crystals come out looking the same. They just don't. I mean, for the most part. Yeah, there are some turnkey, push the button, out comes this thing. It's pretty close. But understand that, crystal growth development, let's just use something like quartz has been researched since crystal growth since like 1906, or maybe even further back. And so, there's lots of variabilities.
So you said post World War II, quartz was really kind of the first mass production effort. What drove that? Why was it quartz?
So quartz is one of the couple of crystals that Mother Nature has made. Again, high pressure water, and then you're able to mine quartz crystals out. But quality wise, they're not so good. So you have to be selective.
Mm-hmm.
Now, quartz again are used in making frequency locked devices, right? So radio station, or
Right.
more importantly, in the military, is radar frequencies, right? So for many years, they used natural occurring mineral, but then once that starts depleting, or it's in a country that doesn't like you anymore, you have to grow it. And that was probably really pushed and pioneered in the 1950s.
That's fascinating. When were dopants introduced?
Probably at the dawn of crystal growth, synonymous with crystal growth, because you're always trying to get rid of them, but you're also maybe trying to add them equally to change the properties. Color centers. If you look at ruby, natural ruby is basically sapphire, aluminum oxide with just the right amount of chromium in it.
Right. Okay, size. The crystal that you showed, 2 kilos, that sucker was pretty big.
Yeah.
So what's the, without revealing any, super secret information, like what's like the biggest we grow and the smallest we grow? What's the spectrum of a mass?
So, I mean, yeah, I'll say for us in New Jersey, we're probably around 30 to 50 pounds.
Wow.
Maybe we could get to 80 pounds, which is about, larger than a bread box kind of thing. Externally, other crystal growths, I mean, silicon is growing like, I don't know, 8 feet long, 12 inches in diameter, hundreds of pounds, right? In contrast to Mother Nature, there's a place that was found about maybe in 2000 from a bunch of mining in Mexico. I think it's Nicaea. Mexico, where they have gypsum, which is a calcium sulfate crystal. Again, hydrothermal, but Mother Earth. Picture a giant cave. They actually call it the Crystal Cave. It's like, I don't know, 700 feet under the ground. It's super hot, but they have crystals with people like climbing around them. They're tons. They're like Egyptian pyramid size crystals.
Now, how long did nature take to grow those?
Great question. The growth really has a lot to do with the quality. Hydrothermally, probably, I would say to get those size crystals, again, they're like 3 feet in diameter and 100 feet long. They could probably grow over tens of years, or depending, again, if you get a big cluster of stuff. I mean, you could precipitate or crystallize stuff out very quickly, but that doesn't mean you're going to get what you want and the quality that you want. It's kind of like you could bake a cake in 5 minutes. You put it in a blast furnace, right? Ain't going to taste good. It's not going to look good. It's going to be, parts of it will be cooked though. But if you really need to cook it correctly, you may have to take 4 hours, right?
Got it.
So just it varies in the quality, time. We grow crystals that take a day, and we grow crystals here in New Jersey that take 6 months.
Okay, so now let's go back to that crystal cave as an example, or
Sure.
basis for my question, which is, can you harvest? Let's say take one of those 5 foot in diameter crystals and you just lop it off. Will it just keep growing? Kind of like
Oh, no. These already have grown under high water pressure when the
So they're being
caves were
revealed.
filled back
Yeah.
1,000,000 years ago, plus the pressure, water, and then it cools, and then the water goes away, and now you actually could touch and see the crystal. So the crystal growth is completed. The crystals are extracted by Mother Nature getting rid of the water.
So, and you brought up silicon, right? That was an interesting one too, because think about it. It's like those big giant, I think they're called bools, right? When they're in their,
Pools, correct.
yeah.
Yep.
I mean, we talk about Moore's law all the time and increasing wafer size yields, economical advantages that then drive performance. But you can't get there unless you have the wafer size to support whatever process you want to put into practice. And that depends on a natural process, which is now being replicated by man in order to achieve that goal. So in a way, it's the most fundamental process, which then drives the fantastic advances we've seen in the industry as a whole.
Correct.
Never thought about it that way. I mean, and I've seen those bools before, and they are pretty amazing looking. And I also know like processing it is really interesting. I've learned more about that in the last few months about the cutting and flattening them. That's a really cool area.
Right.
Okay, so let's talk about manufacturing crystals. So you mentioned one, and I know there's like chemical vapor deposition's another one. What are the major processes for manufacturing crystals that are in practice today?
Okay, great question. So I mentioned earlier when we were talking about Mother Nature, Mother Nature is basically two main ways. One is the hot lava cools, and you get the zircon from 4 billion years. That's stuff that's actually dissolved in hot lava, right? Materials. Probably the second most is hydrothermal, and what that is you take water, simple, right? A lot of water. You put a lot of pressure and a lot of temperature, and believe it or not, it can dissolve just about anything on the earth, anything. And then you cool it down, maintaining that pressure. You heat it up, it dissolves, it becomes something called a superfluid, which maybe we'll talk about another time. But then you basically, crystal growth happens by, it starts cooling and the material doesn't want to be in the liquid anymore, and it starts crystallizing out.
Equipment. Now, let's say I want to start a legitimate crystal growing business. This equipment, I don't imagine I can just go to Granger or Amazon and buy it, right? I mean, this is not only highly specialized, it's probably highly customized as well.
Sure. And again, I talked about the two Mother Nature things. the mankind things is, I don't know, more than on my two hands. Like you could pull crystals like Sikorsky. You can uh, do the lava thing like Mother Nature. You can do again what Mother Nature did with hydrothermal, but controlled in these types of equipment. So the equipment that you purchase, or more importantly, customize, because there's plenty of stuff out there. You want to grow good, pretty decent silicon, you could buy silicon growers. They spent billions of dollars developing these types of techniques. Still, you need to maybe, depending on the type of silicon and the size and the defect concentration you need, you might have to do some research and have some things there. But the equipment is, I would say, available in some genres, but others you basically got to build it all yourself. Like for the lithium borate crystal that I showed you, that's a nonlinear photonic crystal. Uh, we build our own equipment for that.
Huh. Okay, so in addition to the equipment, it seems like the other thing you need in abundance is energy.
Yeah, a lot of electrons.
Yeah,
Yes.
yeah.
Yeah, I mean, I'm talking about high pressures, high temperatures. For an example, we grow sapphire here also. If you dope sapphire with titanium, you get a ultra fast gain material that you can pump and make very broad wavelengths, very short pulse durations, and that is sapphire melts about 2100 centigrade, which is 4,000 ish Fahrenheit, and our grower, which grows a boule about, let's just say maybe 18 kilogram ish, is runs at 50 kilowatts continuous for a month and a half. So our site in New Jersey has about 6 megawatts of power on the input side. So very, very power intensive.
So for facilities, you actually have to plan your facility where you can get good power, reliable and quality, good quality.
Yeah, well, basically, we're set up here. Any good crystal growth building or infrastructure is kind of like a data center. It can't go off.
Right.
If the power goes off for 1 second, in most instances, what you've been growing is ruined. So basically, it's like data loss. So we have redundant UPS, about 3 megawatts of UPS capability here.
I was going to ask because I have a whole house, because we live in Florida where hurricanes, so we have a whole house generator, and I'm just like doing the math, like how big would the backup generator need to be for that?
They're pretty big. We have two 16-cylinder, each are a megawatt. The reason why you have two is you need redundancy. In UPS world, one is none, right? So one's got to be getting fixed, and the other one's got to be there in case there's a power outage. But you need a little bit more than that. A generator takes time. When the power goes out, like in your house, it goes dark for like 10 seconds or so, and then the generator comes on, and the transfer switch. We actually need batteries also, so that it's actually uninterruptible. So the power goes out on the line, and you don't notice it. You don't even notice it.
Yeah, yeah. Okay, so we've got a ton of electricity. We've got some really specialized machinery and a facility that's built for this kind of operation. What are the raw ingredients that you need?
Well, that's kind of like a question of what kind of cake you want to make. I mean, if you're growing oxide type stuff, I would say what we're doing here is oxide based. We do some fluoride based. So raw materials are pretty much limited to the non-radioactive area of the periodic table, from lithium, borates, aluminates, fluorides, calcium fluorides, those types of things is their rare earths, and you source them globally.
Okay. And so, and I would imagine some of this material in its raw form can be pretty toxic too, right?
Yes, there are, things to consider with respect to, um, I would say, if we look at safety in general. I mean, I mentioned high pressures in hydrothermal. We don't do any hydrothermal in New Jersey. That's done quite a bit in the obviously in the quartz processing around the world. That's water at about 300-400 degrees centigrade and
Wow.
30 to 60,000 psi. So you really have to design your safety into your process. And I just want to underline it's paramount to always have a safe process, and that really depends on the type of crystal growth and what you're putting in there.
So the most precious asset in this whole process, though, is the human knowledge that goes into it. And I've met some of the people on your team over the years, and
Mhm.
the thing that's always struck me about it's, Coherent really does feature a tremendous array of people who are just incredibly passionate about what they're doing. The Crystal team, I think, takes that. It's like 11. You just go to 11. They've devoted their lives to this area of science. Um, so when you look at the human capital, now there are different roles in the process, different steps, but basically you have to have people who understand, like you said, curious, like they're watching something that's happening and they're able to react to it, because this isn't a formula. It's not like a bake where you just put it a cake where you bake for 26 minutes with these ingredients. There's a lot of variability that can happen here as you're processing it, right?
Yeah, I mean, again, the cake analysis holds here.
Yeah.
I mean, we have to do the same things. We got to batch it all up. We have to monitor it. We have to look at it when we can. There's actually some processes, sorry, that we do that you can't see. In other words, you got to wait. Like that beautiful crystal that I show you. Let me just pull it up real quick here. So this sucker is grown within a flux, so in liquid, up to about here, right? So you can't see this. You can't see all. So you see me through here, right?
Yeah. Yeah.
You can't see what's going on underneath. You have to wait 6 months before you see whether you got thumbs up or so looking at the dynamics of the growth itself uh, requires people who have some materials background, requires people like we say are curious to especially in the engineering side. You don't want in production, you don't want them too curious, right? Because then they're turning knobs. We've got a
Yeah.
whole different issue. But overall, the crystal growth really is, again, I used the analogy prior about like flying a plane. You got your instrument clusters, right? But every time you grow a crystal or you fly a plane, it's a different adventure.
Well, I think that's true, because the most important thing about flying a plane is knowing what to do when something goes wrong, right? It's like when everything's
Correct.
going right, yeah, it's good. But when something goes wrong, you really want someone up there who's got the experience, says, oh, yeah, I've seen that before. What's the most difficult crystal to produce? And I'm going to I'll be very vague about defining difficult. So you can define difficult however you want.
Well, I mean, fundamentally, that's a great question. I mean, we create materials, and mankind, and creates materials of quality and types that is not available in nature.
Mhm.
The most difficult types of crystals to grow are crystals that don't want to exist. So, yep, like not found in nature. Okay, check that box. Not found in nature. But then there's something called phase diagrams, which kind of shows you if you put, component A and component B together, they form, and they're happy, and they're happy. But then there's a region where they're not happy. They don't like to form anything, or if they do, it's only in a small little region of their phase diagram and composition, and you kind of have to try to grow it right there, and then God forbid, there's also things in materials called different crystal structures or phases, right? Like, ice melts at zero or freezes at zero, right? Well, maybe just above zero it melts and below zero it freezes. But it's different structures, different phases. So there's some crystals that you grow that, oh, you're all happy, you're growing it here, but then when you cool it down, it turns into something else.
Hmm.
So to simply answer the question, there are plenty of materials, and we grow a couple of these materials, especially in the fluorides, where they don't want to be. You have to, if you cool them down too slow, it's something else. If you grow it with the just off a little composition, it's something else. But if you do everything just right, you get it.
So a big part of, so if I interpret what you're saying, like a big part of what you guys do is also pushing and figuring out how to make those things that don't naturally go together for our unique purposes.
Correct. Yes.
Okay, lab-grown diamonds, they've become pretty popular in culture. At first glance, I would think, well, that's kind of like far afield from what we're doing. But after listening to everything you've just shared, not really. I mean, we are growing diamonds as well, right? But we're just doing them in a different form.
Yeah. Well, there's maybe two types of ways to grow diamonds. Our group in Saxonburg does, chemical vapor plasma deposition. So you're growing them basically using a lot of energy with respect to temperature and plasma and vapor transport. That gives you good quality, high quality boule material. Then there's another method where founded by the Russians many years ago, where basically you just kind of put it's actually lava or flux growth with a little seed and a little capsule of I think they use boron nitride under these giant anvils of pressure made out of tungsten, and then they heat it stupid hot, and then they cool it down with the temperature gradient, and they grow off a little seed, and they can grow carrots in like a week, a couple of carrots. It's really amazing, and that's really like gem quality. Like there's laboratory grown diamonds. That's the typical process. This big anvil thing.
Yeah, my wife asked me about that because she heard me talking about, that our diamond product. She's like, really? I'm like, yeah, here's a picture. And she's like, that's not a diamond. I'm like, well, no, it's a thermal device that's, a
Right.
a thermal component. And I'm like, it doesn't look like the diamond that you'd be interested in, but it's a diamond.
Well, unless it's like you need a black diamond. Those are sometimes popular.
Yeah, yeah. Space. I know there's been some experiments about growing crystals in space.
Yes.
Is there there? Is that going to happen?
Well, it has happened. They call it crystal growth or microgravity crystal growth. We've done it on the space station a number of times. The materials, basically, they were growing fairly lower temperature type materials because again, we were talking about all this energy. Yeah. And on a spacecraft, you don't want a lot of weight. You don't want a lot of energy. You also don't want it to catch fire, right? Or anything like that. So they're not doing sapphire. They're doing things that I think were a couple hundred degrees, maybe 400 to 600 in that region. Kind of just about glowing kind of things. And it was semiconductor type materials. And what they found out is that actually the defect concentration, due to being in microgravity, actually produced some pretty nice stuff, like in certain areas under certain conditions. However, manufacturability, not at this time from a cost perspective. Right? Mm-hmm. So, I mean, it's been done. It's really cool stuff, but I don't think they're continuing this at this time. I could be mistaken with that, but I mean, I think it's demonstrated that there is the ability, if we ever do manned flight on the way to Mars and we need to grow some crystals, we can, and they'll be good quality. But to do it and then bring it back to Earth, I don't think the cost and need model works at this time.
All right. So my last question, and it kind of goes back to the beginning, which is the capacity for human innovation always inspires me. So if we can figure out how to grow crystals, can we also eventually figure out how to produce precious metals, rare earth minerals, things that are in otherwise precarious supplies, to ensure our progress to the future?
Well, crystals are made from elements, right? Atoms, right? I mean, sorry for the props here, but atoms,
we love
right?
props.
You got oxygen and you got carbon. This is actually, I don't know what it is. I think we had some kids come over and we had to bring your kid to school day. So we made molecules. So crystals are made from the elements, right? Like the lithium borate crystal I showed you, the big, nice, pretty clear thing. That has got lithium ions, boron ions or elements, boron, lithium, and oxygen. That's it, just those three. And they're in a orthorhombic crystal structure, right? I think maybe with big particle accelerators, you can actually change the elements to other things, but real expensive and not a very efficient way to do these things. Like, I think you can make lead into gold, but I think it takes like $1 billion or something to make a gram.
Yeah.
Right?
Well, if the price of gold will go in the way it is, it might actually be economical at some point.
Right.
Dominic, like I said, I've been wanting to do this talk for a while because this area of the business is absolutely fascinating to me, and I hope it is for everybody who's listening. I want to appreciate you for taking time. I know you're super busy, and to take an hour out of your day is really generous of you. Thank you for joining us.
Well, thank you for the opportunity, Jeff. I'm never too busy to talk about my passion on crystals and materials. Thank you for the opportunity.
Now Next and Beyond is hosted by Jeff Nolan, produced by Carly Burgall, and presented by Coherent.